So now we're going to look at the same problem and compare it in how we are going to solve it for the ideal versus actual. So now we have parameters of pumps at 75% and the turbine at 60%. Therefore, this is what we have. So now, suppose the efficiency of the pump is at 75% and the turbine is at 60%. Meaning, all of the pumps have 70% efficiency and turbine has 60% efficiency. Therefore, you must not forget the formulas is that this is enthalpy of ideal, actual, and for pumps are enthalpy of ideal over actual. So, this is not it. Now, looking back at what we have work of the pump at 0.39. Therefore, if we want to know the actual work, what happened is that work pump 1 is equal to this is the efficiency, this is the work of the actual pump. Therefore, we have ideal, which is what is our ideal work pump. Work pump prime na lang. So 0.39 over its efficiency of 0.7. Therefore, 0.39 times divided by 0.7 yields a bigger one of 0.5571. So work pump 2, same as also 1.19 over 0.7. So 1.19 over 0.7 will yield to 1.7. So meaning it is higher. Work pump 3, also the same. So 20.10 divided by 0.7 will yield to 28.71. Work pump 4 now is something. So 12.38 divided by what? 0.7. So work pump 4 is now equal to 17.69. So this is now our work pump. So I just simplified it so it would look better. So we have now the actual work pumps. Now we can now solve for the actual enthalpies. But for our givens, unless stated, the actual enthalpies are just useful in here because here we could not use them at all because they're not really that useful. Because we still assume that the masses, but let's just assume that the masses stay constant because if there is an efficiency deficit, therefore the masses will also change. But here we let's not assume that the masses still are the same. So now we're going to look at this. Each one of the expansions of the parts. So first of all, we need to find the work of the turbine at the first stage. Therefore, we need to subtract H9 minus H10. H9 is, I'm not going to write it anymore, 3582.3 minus 3153.25 is having a work of 429.5 0.05. So that's the first, or stage 1. So work of the turbine at stage 2 is 12 minus 13, but with 1 minus 1. Why? With 1 minus 1. Why? Is because we bleeded it there. And we have known that 1 minus 1 is 0.97 from our given. Therefore, we can write work 2 as 12 minus 13, which is 3674.4 minus 3325.20 times 1 minus 0.097. Therefore, we have a work of 315.32. So we have work total of 3. This was included with the masses. So yeah, work of 3 at turbine 3 is 14 minus 15. So we got 3694.4 minus 3231.90. So we got 462 times 1 minus 0.097 minus again 0.08. Therefore, we have a work here of 380.64. So work turbine at 4 now is 16 minus 17. So 16, 3702.4 minus 3220.51 times 1 minus 0.097 minus 0.08 minus 0.112. Therefore, our final work here is 342.62. Yeah, that's the thing. So here are our works in total. So now we need to find the total work of the turbine. So we just all this. So the total of this is now 429.05 plus 315.32 plus 380.64 times 342.62. We have the total work of the turbine at 1,530.99 kilojoules per kilogram. This is the actual work that happened to a turbine. So that's the actual work. Work turbine. Oh no, ideal. This is the ideal work. Sorry, 1530.99 kilojoules per kilogram. So good. Now we need to convert this into actual works. Therefore, to convert it to actual works using our formula earlier, we just multiply this by our efficiency. So we have the efficiency of 60%, so we need to find the efficiencies here at 60%. So 429.05 times 0.6. Therefore, because it's really inefficient, 257.4. So now we have 315.32 times 0.6. So we have now a 189.192. So 380.64 times 0.6 again. So we have 228.384. And 342.62 times 0.6 yields 205.572. So now we have the work of the turbine. So good. So work turbine actual at net. So we add this all, 257.4 minus 189.192 plus 228.384 plus 205.572. So we have now a really bad number, a really small number. This reflects 60%, so 54.8. kilojoules per kilogram. So this, we have now actual numbers. So if we have actual numbers, then we could not always, because there's an actual, if we are going to look at this again, there will be a deviation of this thing. Therefore, 13, 10, 13, and 15 will move away. And this will also move away. So therefore, making us new parameters of actual 10 prime, 13 prime, 15 prime, and 17 prime. So now with this new work, we can now find for the new enthalpy of 10. Because we have the new work, the boiler heat does not change at all. So writing the formula now to find the new enthalpy at H10 prime. So the actual work now is H10 prime is equal to, what is the enthalpy again? The enthalpy at 10 minus the ideal work. Because we know that ideal work is equal to 9 minus 10. So 9 minus 10 is equal to work. But now we have the ideal work now. Therefore, we need to find 10. So 10 would be moved to 9 minus work is equal to 10. So H10 prime is equal to, what's H9? 3582 minus work. So minus 257.4. So 3582 minus 257.4 yields us a lower number of 3324.6. Same with this one. Instead of H10, we are finding for H13 prime. So now H13 prime, we need to get H12, which is 3674. 3674.4 minus 189.192 yields a lower amount of 3,485.208. So now at work at turbine 3 is at H15 prime. So H15 prime will yield to H14, which is 3694.4 minus 228.384. Now we got a lower number of 3466.016. And H17 prime now will yield from 3220.51 minus 205.572. We now have an enthalpy of 3.071 014.94. So these are the actual enthalpies of that thing. Now, because we have the actual enthalpies of that thing, we can now solve for the Qins, the total Qin. So Qin is now equal to the same, but instead of using the ideal, we are going to use these values. So what's the highest of this? 9. So we are just going to plot it in our calculator, same as earlier. So we have 9, which is 3582.3. 3582.3 minus, what is the new, what is the old one, which is just the same. So H6 or H7 is 864.99 times 100, because 100 is the mass. And so plus what? Or let's just not add 100 for now, because we can just add 100 later. So now plus, we have now the new one, which is 12 minus 10 actual. So 12 now is 3674.4 minus 3485.208. Right? Yep, that's right. So 1 minus 0.097, because we assume that it's constant. So therefore, H14 is 3694.4 minus what? 3466.016 times 1 minus 0.97 minus 0.08. And lastly would be the Qin of 16, which is 3702.4 minus, instead of 3220.51, we get 3446.016 times 1 minus 0.097 minus 0.08 minus 0.112. Therefore, we got a total Qin of 3,258.40 times 100, so we can get the megajoules of that thing. So megawatts, so 325.84 megawatts. That's our Qin. You see, this is lower compared to this one, so therefore we're going at the right track. Now Q out. Q out is now useless, is because we're using actual. We cannot use the 1 minus Q out over Q in because that only works for an ideal answer. Now we are in an actual answer, so we're going to tackle it using work net. So we have Qn. So we have now work of the pump's total of actual work pump. Therefore, work net is equal to work turbine actual is just 680.50 55 times 100. Yields a really small amount of 68 megawatts minus finding the total of this, so it's 0.5571 plus 1.7 plus 28.71 plus 17.69 times 100 yields 4,000 or just 4.87 megawatts. So this will be our new work net, which is 68 minus 4.87 yields 63.13 megawatts. So this is our work net. After we got our work net, we now solve for the efficiency using work net. So efficiency now can be solved as efficiency is equal to work net over Q in. Notice that our work net is really small, 63, compared to work net that we have earlier, which is 100 plus. 6.13 over 325 will yield us 63.13 divided by 325 will yield us a really bad number of 0.1942. Therefore, its efficiency is really low compared to its original efficiency at an ideal of 42.72%. So this is how you solve for an actual Rankine cycle involving reheat and regenerative, assuming that the masses do not change. But in an actual scene, within actual enthalpies, masses do change. And what do you mean masses do change? Because we adjusted the enthalpies here and the enthalpies there, masses also adjust depending on how we extract them. But sometimes, due to better engineering, we do not, or the masses do not change. Even in actual, we calculate for the pressure loss and the temperature loss of the pipes and whatnot. But for now, we are going to delve more on the theoretical part of reheat and regen of thermodynamics 2. So that's all. Thank you for watching. I hope you learned something.